Yeah, so we are finally starting. Today, Ahmed. Guys.
Beginning.
So so we are starting. I'm sorry for the delay. Today, Ahmed Maghri is gonna talk to you about the mathematics behind machine learning, a topic he's very passionate about. He's studying it. He's a CA's major. I think he's one of your TAs, and he's very excited to talk to you about this today. So hope you enjoy.
So, hello everyone. Hope you're all doing well. As she said, I'm Ahmed Maghri, computer science major and the mathematics minor. So today is going to be our first episode of our series of topic tutorials we're preparing with the Math Society, namely called the Math Behind Artificial Intelligence, Neural Networks, and Machine Learning. During this talk, the point is that a lot of people here think that AI is, I would say, some magic, like we don't know what's happening behind it. I want people to leave the room knowing what's actually happening behind AI, to understand it's just some equations they have to optimize, and to know what's really happening behind the scene. So, I thought about how should I organize this presentation, right? I mean, I didn't want to make it boring. Okay, sorry. No, it didn't go. No, it's fine. So the way I organized this whole presentation is as I were discovering a galaxy that I namely called AI 404. We're gonna explore each planet, and each planet has some properties, and we're gonna understand what each one offers. So let's start with the first one, namely called the premises of AI. AI is surprisingly actually a very old subject. It existed since 90s, 80s. A lot of people try to solve problems with AI. But from the beginning, I'm talking about AI. A lot of people maybe here don't know what's exactly AI. So let's all agree on what's AI. So, artificial intelligence, scientist agents that perceive the environment and act rationally to achieve some goals. And the point is, what goals? That's the first question. What are the goals that people needed to solve at the 90s? Surprisingly, one of the first examples that they tried to solve using AI is solving a maze. So let's consider an example. Let's consider that we have such a maze, and we will try to solve it using AI. So one of the most classical way to solve AI is what we call depth first search algorithm. So what does depth first search does? The first question that we have to ask ourselves is, what do I do when I reach a fork? Because here it's very obvious that we're just going to go directly, right? But should I go right or left? That's the question. So what depth first search does is that it just goes randomly, read either right or left, and goes until it reaches a dead end. So for example, let's assume that it picked randomly left. So it's going to go left, 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 and then reach a new fork. So then either could go left or right again. So for example, we would go left and reaches a dead end, then we'd go right, then okay, it's going to come back to the previous fork, then we'll go to the next fork, and then we're going to be like, okay, I go up or right, let me choose right, why not? Then I go, the boom, next fork, and then I have to go down or right, let me choose right again, then I go here again, I could go up or down, and for the sake of the experiment, maybe the AI chooses top randomly, and then I'm going to come back to the previous fork, and then going to go down, and then going to continue until it reaches the exit point. Which works. Our AI found the exit, actually, right? The problem is that it doesn't always guarantee that we find the shortest path. If you consider, for example, such a maze. So our depth first search AI could go either up, could go right, and it's pretty random. So let's assume that the AI decided to go up. Then it will go this way. Then, for example, let's assume that it decided to take the right path, and then again the down path, and then it have the exit. But we could tell that this is the shortest path, right? We know that this is shorter than this. So we want to now guarantee that our AI model is going to be able to always find the shorter path. And then another algorithm has been invented to solve such problems, what we call breadth first search. What does breadth first search do? Is that instead of going until a dead end, it goes in the same manner in all the possible paths. So for example, here it will go one step right, one step up, then 2 steps right, 2 steps up, then 4 steps right, 4 steps up, and then it's going to go each time adding the exact same amount of steps in all the possible directions. And you could see that here, it's guaranteed that we had the first and shorter path. Better, right? The problem is that even breadth first search had a caveat. So for example, if we come back to our previous method, and let's try to execute breadth first search again. So first, we come to the first fork, and then instead of going left or right, it's going to go in the same manner in both directions. then here it finds a new fork, and then goes in the same manner in both directions, and then it fills all the possible cases, and then reaches the next fork, then go the same manner in both directions, and then reaches a new fork, and then go in the same manner in both directions, and then there's no fork anymore, that continues until it reaches the end. The problem here is that it needed to explore all of the maze to find the answer, which is very computationally heavy. We don't have time for this, and we want to optimize this. We want to make it more efficient. So let's try to give it some intelligence. If I was a human and I look at the maze, me, a human, I am able to say, okay, if I go here, I am somehow getting closer to the exit point, right? That's the intelligence that we want to give our AI. We want to make it able to predict how far we are from our exit point, what we call a heuristic. So our function, h, that takes as input x and y, which are the coordinates of our maze, gives you as output distance that you have between the case and the exit. For example, if you take h of 3, 2, the distance between this point and the last one is 12. So what we're going to do now, we're going to compute the heuristic in all the possible forks. So for each fork, I'm going to compute the heuristic in all the paths. And then we compute an algorithm, or we execute an algorithm that is called greedy best first search. What does greedy best first search do? In each fork, it goes in the path that has the least heuristic, which makes sense. I'm going to go in the path that makes me get closer to the exit. So first we'll go to this side, so the 11 one, then we're going to go to 8, could choose this one or this one, it's pretty random. Let's assume that it took this one. Then 7 has 8 and 6, going to take 6 because 6 is smaller. Then 5, then it has 4 and 6. And even if this has a dead end, it doesn't know. It's going to go to the lowest one. So we're going to go to 4 first, and then going to come back to 6 and reach the last one. We could see that it's better. We explored less, and we arrived to the final point easier and faster. And it always guarantees to find the shortest path. Or does it? If we take, for example, such a maze, and again we compute the heuristics. If we execute greedy best first search again, it's gonna take the path that has 11 heuristic, because 11 is just less than 13th. But we know that this path is shorter. So now we have to add, I would say, more intelligence. We have to make the AI understand the costs that I need to go to that path. Is it worth that I go to this side? So people come up with another algorithm that is even, I would say, smarter, that we call A-star search. A-star search is a search algorithm that expands the node with the lowest value of an, such that an is equal to gn plus hn, where gn is the cost to reach the node, and hn is the estimated cost to the goal, which was our heuristic. So if we try to, for example, do A-star search on our previous maze, instead of computing only the heuristic, we would compute what's the heuristic plus how many steps I need to do to arrive to that case. So when I arrive here, I have 11 plus 6, which is 17, 13 plus 6, which is 19. So this is still smaller, so I'll go this way. So I'll continue, 10 plus 7 is 17, still less than 19. I'll go this way. 13 plus 4 is equal to 17, still less than 19, I still go that way. But 15 plus 6 is equal to 21, which is bigger than 19. So instead of continuing this way, I will go back to here. So it continues here. 7 plus 14 is equal to 21, which is equal. And even if it continues, this gives 22. So it's going to go this way. And then it's still 21, 11 plus 10, 21, 19 plus 9, 21, and it stays 21 until we reach the end. More intelligent. Now we're able to find the shorter path, always and efficiently, and we don't need to explore the whole map. So that was the beginning of AI. People trying to reason with simple steps. The problem is that if you think about it, our AI doesn't really reason. It doesn't deduce stuff. It only uses the data that it has on the moment. It doesn't have previous data and they're like, okay, I knew this, so this may imply this. Moreover, our AI only gives us, I would say, direct solutions. It doesn't say, okay, so this solution most likely be true, for example, right? The whole other planet is about this most likely, which is probability and uncertainty. So we're going to try to make our AI have some probability inside of it. Make it reason and make it say, okay, this solution may be the most probable one, or this one maybe is less probable. And make it reason, having some previous data. From this previous data, I can understand maybe this is going to happen. But to talk about probability, I have to talk about one essential object. That is the key object in probability and uncertainty, which is namely called random variables. So what's a random variable? Random variable is a variable that can have n possible outputs. For example, if we check the variable roll, assuming the roll is the output of a dice when you roll a dice. This output could take the value 1, 2, 3, 4, 5, 6, for example. If we consider the random variable weather, the weather could be either rainy, have wind, snowy, cloud, or sun. If we consider the variable traffic, the traffic could be none, light, or heavy. That's the first step. Second step is that how do we compute probabilities with random variables? Usually, for example, we say that the probability of the traffic being equal to none is 0.2. The probability of the traffic being equal to light is 0.7, and the probability of the traffic being equal to heavy is 0.1. Remark that the sum of the probabilities is equal to 1, which is very important. And these three numbers are what we call a probability distribution. We say that probability distribution of traffic is equal to 0.2, 0.7, 0.1. Of course, we agreed on the first slot expressing the known, the light, and the heavy. Then we talk about conditional probabilities, which is really going to make us reason. So knowing this, I can deduce this, which is conditional probability. For example, we denote here that what's the probability of the traffic being equal to heavy, given that the weather is equal to snow, which even could be simplified as just probability of heavy given snow. Now, we have our foundations of probability. Let's try to integrate this in our AI. So, during exploring this planet, we'll face three main, I would say, topics. And the first one is called a Bayesian network, which is a key thing that makes us really make the AI deduce and reason. So what's a Bayesian network? It's a direct graph where each node represents a random variable. An arrow from x to y means that x is a parent of y. Each node has a probability distribution, probability of E of x, knowing the probability of parent of x, given the parent of x happened. Pretty abstract, so let's take an example. Let's assume that we have such a Bayesian network. The root node is rain, doesn't have any parent. And rain could take the values known, light, or heavy. Then we have the variable maintenance, which could be either yes or no, so either the maintenance is happening or not. Maintenance is only dependent on the rain. Then we have the variable train, which could be either on time or delayed. Then we have the variable appointment, which could be attend or miss. Notice that appointment only depends on train, while train depends on both maintenance and rain. As I said, in the definition of Bayesian network, each node has some probability distribution dependent on its parent. If you take, for example, the node rain, it's a root node, so it doesn't depend on anyone. So it only has its own probability. So the rain could be none, and let's, for the sake of an example, let's say that it has 70% chance that it's equal to none, 20% chance that it's light, and 10% chance that it's heavy. If you take the node maintenance, it depends on the outcome of the variable rain. So for example, we say that if rain is equal to none, then there is 40% chance that maintenance is equal to yes, and 60% chance that it's equal to no. If we take, for example, the rain being heavy, then we have 10% chance that it's yes, and 90% chance that it's no, which makes sense. You wouldn't do maintenance on a very rainy day. Then, if you take the next node, which is train, it depends on both the outcome of maintenance and rain. So, for example, we say that if rain is none and maintenance is happening, then the probability of the train being on time is 80%, and the probability of the train being delayed is 20%. For example, if I take this example, if the rain is heavy and the maintenance is happening, then the probability of the train being on time is 40%, and the probability of the train being delayed is 60%. Then the final node is appointment. Appointment only depends on train. So, for example, we say that if the train is on time, then there is 90% chance that I attend my appointment, and 10% chance that I miss my appointment, which makes sense. If the train is delayed, then I probably miss my appointment. That's why when the train is delayed, it's 60% chance that I attend my meeting, and 40% chance that I miss it. And only with these probabilities, we could already start reasoning using the Bayesian network, using what we call joint probabilities. So, to compute joint probabilities, we use what we call the chain rule of probability. We say that, for example, that the probability of x1 happening and x2 happening until xn happening, so x1, x2, xn are all possible events, is equal to the probability of x1 times the probability of x2 given x1 times the probability of x3 given x2 and x1, all the way to the probability of xn given x1, x2, all the way up to xn minus 1. Pretty abstract again. So let's take an example with two events. For example, we'd say that the probability of x1 and x2 both happening is equal to the probability of x1 times the probability of x2 knowing x1. Then, For example, if I want to tell my AI, okay, so what's the probability and how likely is it going to happen that this day is going to have light rain, no maintenance, and the train is going to be delayed. Using the chain rule of probability, I can conclude that it's equal to probability of light times probability of no maintenance given light times probability of the train being delayed given that there was light rain and no maintenance. And all these probabilities are already given with the Bayesian network. So I can directly compute it if I give it to my AI. Then, for example, that's when we start talking about inferences. So inferences are basically the second part of the planet, and when you know something, so I'm given a question and I'm given an evidence, and I try to know what's the answer to the question given the evidence. For example, if you have such a query, for example, what is the probability that I miss my appointment? And I'm telling my AI, there is no light rain today, there is light rain today and no maintenance. First of all, the first step is let's try to change this natural language problem into a probability question. So the probability that I miss my appointment is equal to probability that I miss my appointment, given that there is no light, there is no maintenance and light rain. But the appointment variable is not related to these variables, right? So I can't use the previous technique that I used. So first of all, the first step is that we have to convert this conditional probability into a joint probability. And then we use a rule of probability which says that the conditional probability is proportional to the joint probabilities. And then we use another trick that's called marginalization, which means that I take the same probability and I say, okay, this probability is equal to miss, no, and light, and the train being on time, plus if the train wasn't on time, which makes sense, right? The train is either on time or delayed. So this should be normally equal to the last one. And that's why I always start to reason using the Bayesian network. They're already big progress. Now our AI is trying to reason, right? So let's try to tackle another type of questions. Now, let's try to answer the question, what's going to happen today, knowing that this thing, for example, happened yesterday, and the day before, and all the days before, for example. What we use to solve such questions is what we call Markov chains. So what are Markov chains? So Markov chains need what we call a transition model. Markov chains try to create some, I would say, relation that predicts what's going to happen tomorrow based on what's happened today or the day after. And the transition model serves to say, for example, if today was a sunny day, then tomorrow I have 80% chance of being sunny and 20% chance of being rainy. While if today was a rainy day, then tomorrow I have 30% chance that it's sunny and 70% chance that it's raining. And to make a Markov chain, we rely on one big assumption that Markov assumed, which we call the Markov assumption. So it says that the probability of today's event, given all the events that happened before, is equal to probability of today's event given yesterday. What it means is that today's event is only dependent on yesterday. That's what it means. And then we can start making some Markov chains, for example. It could be an example of a Markov chain. So today it was sunny, and tomorrow it's going to be sunny, and tomorrow it's going to be rainy, tomorrow it's going to be rainy, tomorrow it's going to be rainy. The problem is that you could already notice that it's not very accurate. And usually, me, for example, as a programmer, I don't really know what's the hidden state of the weather. I don't really know what's happening. Let's say I'm in the office. I don't know what's the weather outside the office. So we can use, I would say, some sensors. For example, for the robot's position, which would be the hidden state, I can use the robot sensor data. For the word spoken, I could use the audio waveforms. For the user engagement, I could use the website or app analytics. And for the weather, we use umbrellas. What it means is that I can try to approximate what's the weather of today, knowing that, for example, how many people bring an umbrella to the office. For example, if a lot of people bring an umbrella to the office, I could tell that it was probably a rainy day, or at least maybe there was a lot of clouds on the sky. So then, to this transition model, we add what we call a sensor model. So for example, the sensor model says, okay, given the observation that today people bring umbrellas, then it means that the probability that today is a sunny day is 10%, while the probability of today being a rainy day is 90%. While if people didn't bring an umbrella today, the probability of today being a sunny day is probably 80%, and the probability of today being a rainy day is 20%. Then you could create, I would say, upgraded Markov chains, for example. I'm trying to approximate the actual data using my sensor data. For example, I could tell, okay, people didn't bring an umbrella today, so it was pretty sunny day. And given that it's sunny day, so tomorrow is going to be a sunny day. But tomorrow, people bring an umbrella. So it probably means that people saw, for example, clouds on the sky, and that's why they bring an umbrella. So tomorrow is going to be a rainy day, and people bring an umbrella, and then after it's going to be a rainy day, and people bring an umbrella, and then afterwards a rainy day, and people bring an umbrella again. And we could use such techniques in a lot of tasks. For example, we could use it in filtering, which is given observations from stars until now, calculate distribution for current state. Or prediction, given observation from stars until now, calculate distribution for a future state. Or most likely explanation, given observations from stars until now, calculate most likely sequence of states. Again, we did a very, very big progress. While at the beginning, our AI was only really not able to do inferences. Now our AI is able to deduce stuff. I know this happened before, and this means that this is going to happen tomorrow, for example. The problem with this planet is that it still needs us. I had to give him the vision network. I had to give him the sensor model. I had to give him the transition model. The AI needs me to give him all the probabilities. So our next goal is try to make our model find himself the probabilities. We want to make our model independent, basically, which is going to make us explore the next planet. And I would say the first wise planet, the machine learning planet. So machine learning, it's all about given some data and some levels. I try to approximate a function that approximates the data set. Let me make it more clear. So for example, given this set of data. So for example, January 1 had 93% of humidity, almost 1,000 of pressure, and this was a rainy day. Notice that I won't supervise machine learning. Because in machine learning, there are three main categories. And the first one is a supervised machine learning. Why we call it supervised? Because I am, me, the human, I'm the one who labels the rain. I'm the one who writes in the data set, this was a rainy day, this wasn't rainy, this wasn't rainy, this was rainy. And the point of our model, hopefully, is that it somehow should approximate and tell, okay, if I give it this data, it will find what's the correct outcome, what's the correct level, without me telling him. So, first of all, what's the map? In the sense where we could take the same data set and express it as a map that takes as input humidity and pressure. And then maps if the day is rainy or not rainy. For example, f of 49, 1015.5 is equal to no rain, for example. And us, or the AI model, is going to try to find a hypothesis function, I'm going to call H, that take humidity and pressure and should somehow map in the same manner as F. How are we going to do this? Let's try, for example, to plot the data set. Let's assume this axis represents humidity, and this axis represents the pressure. And me, the human, I labeled each of the data points as blue or red, where blue means that it was rainy, and red means that it wasn't rainy. Let's take, for example, these data points. If I tell you, okay, you think this is going to be blue or red? Yeah, why?
Because in the area.
Yeah, it's very close to blue ones. And actually, you did what we call the nearest neighbor classification. What the nearest neighbor classification does is that it looks at the closest data point of our guess and take the same class. So in our example, it's like, okay, the closest one is this one is blue, so I must be blue too. This algorithm has a problem too. Let's take as example this one.
Red.
Maybe, maybe not. It seems closer to blue ones, but it's very close to red ones. If you follow nearest neighbor classification, it would tell that it's red. But other people would argue, no, it should be blue because it's very close to other bunch of blue ones. So instead of using nearest neighbor classification, we're going to use what we call K nearest neighbor classification. What this means is that instead of looking at the closest data point, it's going to look at, for example, K closest data points. For example, it's going to say, okay, so in this circle, this one is blue, this one is blue, this one is blue, this one is blue, and only one is red. So most likely, I am red too. Okay? The problem with this, actually it's not a problem, but you could have even other examples. If you look at, for example, such a data set, you could tell that I can maybe trace a line here, right? That will potentially separate both data sets, which is actually true. And that's what we call linear regression. Linear regression is all about finding a line that will separate both, separate data in some manner. And if, for example, the data point is lower than the line, then it should be, for example, rainy. If it's higher, it should be not rainy. But how does that actually work? How do I find the line? That's where the math comes. So we have h, which is again our hypothesis function. Our inputs are x1 and x2, where x1 is the humidity and x2 is the pressure. And we know that h should be a line. What's a line? Following calculus, a line is just a linear combination of the inputs. Maybe you're not used to multivariable calculus, but it's pretty much the same. Same when you have a line in 2D, you say that it's equal to y is equal to ax plus b. Then you have two inputs now, and we say that it's equal to w0 plus w1 x1 plus w2 x2. Pretty much the same. It's just what we call a linear combination. And we call w0, w1, w2 weights. And how h is going to map? So basically we're going to say, okay, so h of x1, x2 should be equal to no rain if w0 plus w1, x1 plus w2, x2 should be greater than 0. And otherwise it should be equal to rain. This could be even generalized. I'm not always talking about weather. So this could be, for example, 1 or 0. So it should be equal to 1 if the linear combination is greater than 0, and should be equal to 0 otherwise. Notice even more that we could actually express this as a dot product, where, for example, the first vector, which we call w is equal to w0 plus w1 plus w0, w1, w2, x is equal to 1, x1, x2, then w dot product with x would give us w0 times 1, w0, w1 times x1, w1 x1, w2 x2, w2 x2. And then we call w the weight vector and x the input vector. And finally, I could express this as h parameterized by w is equal to 1 if w dot product with x is greater than 0, and it is equal to 0 otherwise. And we say that h w is a parameterized function by this weight w. And now, the whole question is, okay, if I have w, I would be able to classify if this point is rainy or not rainy. How do I find w? That's the main question. How do I find what's the line? Because if you have a vertical line, it doesn't mean that it's going to efficiently differentiate the data set. So, a famous learning way that we have in machine learning, at least for linear regression, is what we call the perceptron learning rule. So, given the data point xy, update each weight according to wi is equal to wi plus a times y minus h of x times x of I. I probably lost a lot of you here, but if actually you just look at the equation, it makes a lot of sense. Y is actually just our actual value, the value that we labeled, while h of x was our estimate. So it makes sense. Why? If our estimate is lower than the actual value, it means that our wi, our weight, was too small. So we should make it bigger. That's why actual value minus estimate will be a positive number. Then we'll have something positive added to the weight, which would make the weight bigger. If our estimate was too big, and then estimate was bigger than actual value, then actual value minus estimate would be a negative number, right? And then we'd give a negative number plus wi, which would make the weight smaller. And then we repeat this process, repeat it, until at some point we hopefully converge. And that's what we call training a machine learning model. We all heard about these wise words, you know, I'm training the model, and I believe maybe some of you already tried it on Python, for example, and you don't understand what's actually really happening. That's what's happening. A very simple equation that's trying to converge to some weights. Yes?
I have a question.
Yes.
What happens when the actual value is equal to the estimate?
What do you mean?
Over here,
Yeah.
if the actual value is equal to the estimate, then what happens to the weights?
I mean, then if the actual value is equal to the estimate, then our weight was correct. And then actual value minus estimate would be equal to 0. And then it's wi is equal to wi plus 0. So wi is equal to wi. Nothing changes.
Nothing changes.
Yeah, because our weight was perfect. Okay. Very good. So we could tell that our function is as if a threshold function. When it's smaller than some point, we give it 0. And when it's higher than something, we give it 1. Which is very good for classifying. But sometimes we care about how strong is our classification. How blue is my blue data point? For example, if I take such sample data, if you have these two yellow points, you could tell that this one is, I would say, more blue than this one. This one is closer to the line, while this one is very, I would say, inside the blue points. So instead of using a threshold functions, you could use what we call a soft threshold. So instead of giving us either 0 or 1, it gives us all possible real numbers between 0 and 1, which expresses how close we are to 1 or how close we are to 0. Makes sense, right? But the problem with linear regression is that it's not able to solve all possible problems. Because linear regression, at the end of the day, it's a linear combination. It's a linear relation. A linear combination cannot draw a circle. It cannot separate data that is inside of a circle. But we'll soon know how we solve such problems. Now, let's move to another type of problems in supervised machine learning, what we call regression problems. Instead of classifying, maybe I don't want to classify, maybe I want to know some exact value. For example, if I'm a businessman, I'd like to know, okay, knowing the advertising I put, the amount of money that I put in advertising, I'd like to know how many revenue do I get. For example, if I put 1,200 euros into advertisement, I get, for example, 5,800 euros as a revenue. And this is data that I myself inputted. And again, I want to find an approximate function, a hypothesis function, h of advertising, that would approximate me what's the actual function. Which is very useful for businesses and for any people that work in a company, I would say. And linear regression still works. For example, you could find a suitable line that try to approximate our data points. And then we need to know is if our machine learning model is accurate or not. And there are multiple ways to know this. For example, we could use what we call the 0-1 loss function. It basically just gives 0 to all correct labeled data points and gives 1 to anything wrong. So blue should have been 1, then we were wrong. So we would give blue 1 and this 1. So the sum is true. And the higher is the loss function, which means my error is bigger. So I should make it more, I would say, more optimized. And there are other types of loss functions. For example, there's what we call the L1 loss function, which is basically the absolute value of actual minus predicted. And then we have what we call also the L2 loss function, which is the square of actual minus predicted. You could tell that this L2 loss function just penalizes more than the L1 loss function. For example, if the loss here was true, here it would be 4. So I would say it punishes our AI more. Then we can move to the second biggest category of machine learning, what we call reinforcement machine learning. In reinforcement machine,
Yeah, I have a question about the linear regression, about the limitations. You said if it's inside of a circle, then linear regression doesn't work.
Yeah.
In that case, can't we use, like, we have different types of regression, like polynomial regression as well, yeah? Why can't we use a circular regression and then specify?
I didn't say you can choose any other one. I said we solve it later.
Okay.
Well, so reinforcement machine learning, in it, we talk about two main words, which are rewards and punishments. All of reinforcement machine learning is about the AI having some set of actions, taking action, and in this action I could either be rewarded or punished. And I train against myself until I find the correct solution. And how do we do this? We use what we call, again, Markov decision process. So the Markov decision process is a model for decision making representing states, actions, and the rewards. For example, this would be a Markov decision process. In the first action, I could take three different actions, and each one has a possible reward. And each one maps me to another action, and this one also has another reward. And the reward could be negative, which would mean then that it's a punishment. So, to start doing reinforcement machine learning, we need some properties, some data. We need a set of states S. So, we need all the states that our program could take. We need a set of actions of S. So given a state S, what can I do with this state? Then we need a transition model. What's the probability of the next state given the current state and the actions that I can take? And the reward function. What's the reward I'm going to take while me being in this state if I take this action and I land in the other state? Let's take an example. So this is our AI. It's the yellow circle. And it want to arrive to the green square. And the red squares means the punishment squares. At the beginning, our AI doesn't know where to go. It just goes randomly, but it learns. That's the point. First, it would go to the red part, to the red square. Then it learns, okay, I got a punishment. I shouldn't go here anymore. So it goes back and can't go here anymore. then goes another way. For example, goes here. Then could go either here or here. And randomly, for example, goes here. Then again, goes somewhere randomly. Goes here, for example. Then goes again, okay, I got a punishment. I shouldn't go here again. Then it goes back here, and then I can't go here anymore. Then it goes on top, again randomly. And then says, okay, I have punishment here. Shouldn't go anymore again here. Then it goes back. Then it goes directly. Then goes in the square. I'm punished. Shouldn't go here anymore. Then goes down, then goes right, then goes top, then goes left, and then goes inside. So, yeah. Again, the same question. How do we learn? How are we going to make our AI model to learn? And we use what we call Q-learning. So what's Q-learning? Method for learning a function Q of SA, estimate of the value performing action A in stage S. So in action S, I'm gonna take an action A. No, I'm in stage S, I'm gonna take an action A, and this Q of SA should tell me what's the potential reward if I take this action. So the reinforcement machine learning tried to approximate this Q. It tried to find the most accurate reward. So how do we do this? Start with Q of SA being equal to 0 for all possible states and actions. Then, when we take an action, we receive a reward, right? Could be negative or positive. Estimate the value of Q of SA based on the current reward and expected future rewards. Update Q of SA to take into account all estimates as well as our new estimates. Again, a bit abstract. If you look at it more mathematically, you could say that again, we start with Q of SA is equal to 0 for all possible states and actions. Then every time we take an action A in state S and observe a reward R, we update. We update what? Q of SA should be equal to Q of SA plus A times new value estimate minus the old value estimate. While A just means a learning rate. If A is bigger, then this would, I would say, act more on this. For example, if the difference was 2 and A was 3, then I would get 6, and this would make my AI learn faster. But if it learns too fast, then it will go a bit randomly. So we try to find the balance with A. Don't make it too small, because otherwise the learning would be too slow. Don't make it too high, because otherwise the learning would be too high, would be too fast, and would be too random. So the new value estimate is just the current reward plus the maximum in all possible future rewards, right? So our estimate is the reward that we can check, that we're gonna have now, and I have future rewards that I could possibly have, and I take the maximum with them because I want to have the highest reward, of course. And then the old value estimate is, of course, Q of SA itself. Then again, I repeat the whole process until at some point Q of SA converges. So the algorithm that we actually executed before is what we call greedy decision making. As I said before, greedy just take the best possible action in our current state, which is not always good. So this is the model that was trained before, the same one as before. The one as before learned that the good actions are this. So it goes here, this way, goes up, left, right, top. The problem is that there could be shorter path. And that's what we call the contrast between exploit and explore. When our AI exploits, it uses previous knowledge that it has in order to make inferences. When it explores, it tries new strategies, tries new stuff, and hopefully maybe this would gonna give us a better answer. So instead of using greedy decision making, we use what we call epsilon greedy decision making. What does epsilon greedy decision making does? It just means that with the probability epsilon, I take a random move. And the probability 1 minus epsilon, I take the best move. For example, let's say that here I took the best move, and here, with probability epsilon, I took a random move. And I went up. Then I went up again and then right. And luckily, with epsilon greedy decision making, we were able to find a shorter path than before. This shorter than going this way and going up and then going up, left, up. Even better, right? So now that we're done with reinforcement machine learning, we're gonna talk about quickly, not too much because it's a very niche and not very used, what we call unsupervised machine learning. So what does unsupervised machine learning means? Well, before we had supervised, which means that we, as humans, inputted the labels. Now we have no labels. We don't know anything about the data. We have data, but we don't know how is it classified. So a very famous algorithm that used in unsupervised machine learning is what we call K-means clustering. So an algorithm for clustering data based on repeatedly assigning points to clusters and updating those clusters centers. Let's take an example to understand this more. let's say that we have such data. And now we want to apply unsupervised machine learning so that it learns, okay, this group is alone, this group is alone, this group is alone. What it's gonna do, it's gonna drop some random clusters. So let's say for example, drop this cluster blue, this one red, this one green. And then it assigns the colors depending on who's the closest one to each cluster. For example, this one would be green, this is green because it's closest to the green one, these are red and these are blue. Next step is that you center your clusters into your data set. For example, the blue one would come to this center because it should be, I mean, the algorithm says that it center itself. The red one would probably come somewhere here, and the green one would probably come somewhere here. And that's what happens. And then it repeats itself again. So first we reassign again the colors, and then it repeats the same process until it converges and doesn't change much anymore. So that was the branch of machine learning. The problem with machine learning is that it's accurate, it works, but it's not enough. It doesn't work for everything. As we saw before, when we had our circle, our linear regression model wasn't able to decide where should I put the line so that it separates our data. So hopefully, our next planet is going to solve this problem. So let's move to neural networks. So what are neural networks? Neural networks is actually something very old that was actually getting invented in the 90s. And how they did this? They inspired themselves with the human brain. How does a human reason and how does a human think? So human has neurons in his mind. And the humans have very, very interesting properties. The neurons have very, very interesting properties. So the neuron can learn stuff, they can be activated, and they're connected and receive electrical signals from other neurons. And now, we're going to try to make an artificial neuron. Our artificial neuron should model a mathematical function from inputs and outputs based on the structure of the parameters and the network. And this artificial neuron should allow for learning the network's parameters based on the data. That's our goal. We want to create this, and we're going to create it. So, instead of talking of neurons, we're going to talk about units. So units, I would say, it's what we manipulate in neural networks. It's the neuron of neural networks, or artificial neural networks. So we're going to keep the same ideas in machine learning when it has a linear combination of our inputs. So for example, if we have x1 till xn inputs, then we want our unit to output some linear combination of x1 till xn. And still, we're going to use the same activation functions as we used before. So we could use, again, the threshold function, which would be g of x equal to 1 if it's greater than 0, and 0 else it will be equal to 0. We could use what we call the logistic sigma weight, which again gives us all the real values between 0 and 1. And we could even use what we call the real u, which stands for rectified linear unit, which is equal to 0 before some exact point, and then it's equal to x after this point. These are what we call activation functions, and we're going to understand why we need them later. So let's try to make our first neural network. Yes?
I'm sorry to interrupt. Can you give us an example?
Yeah, I'll move to it now.
No, so just before that, so how does the activation function relate to the a certain input? If I take x1, x2.
Sure. So for example, let's assume that the threshold is 5. For example, I'm assuming this. So if the input was 3, then the output would be 0. If the input is more than 5, for example, let's say 7, then the output would be exactly 7. That's basically real u. Okay. So let's try to make our first neural network. So we need inputs. So our inputs are going to be expressed by our units, x1 and x2. Then we need an output, which is going to be expressed by another unit. And then we're going to have edges between these two units. It's going to represent our weight that we're given. So if you remember W0, W1, and W2. And somehow, later, it will learn W0, W1, W2 in order to imitate the behavior of our target function. And he doesn't say how it's going to learn it, but he's going to learn it. Just trust me for now. Okay, let's try to make our first neural network. Let's try to imitate this function. This function maps 0, 0 to 0, 0, 1 to 1, 1, 0 to 1, and 1, 1 to 1. And I hope you all guessed it. This is the OR function. So we're going to try to use our neural network to create the OR function. And how we're going to do this? we're going to give W1 and W2 1 and 1. And we're going to give W0 minus 1. And as an activation function, we're going to use our step function. So for a second example, if I input 0, 0 in OR function, it should give me 0. That's true, because when I input 0, 0, I get minus 1 plus 0 plus 0. And minus 1 is here, so it outputs for me 0. When I input to the OR function 1 and 0, it should output 1. So let's try. When I input 1, I get minus 1 plus 1 plus 0, which gives minus 1 plus 1 is equal to 0, and 0 is right after the threshold, which outputs 1. Then, let's try, for example, instead of imitating the OR gate function, let's try to imitate the AND. How we're going to transform the OR to an AND? We just change W0, which also we call the biases. We're going to change it from minus 1 to minus 2. Then try. If you input 1 and 0, then you get minus 2 plus 1 plus 0, which gives minus 1, then it gives 0. And if you output 1 and 1, then you get 1, 1, minus 2 plus 1 plus 1, minus 2 plus 2, 0. 0 is after the threshold, it will output 1. Again, I'm assuming that my neural network found the weights. It found that it should be minus 2, 1, and 1. The most important question is that how it does it. And that's, I would say, a very, very important algorithm in... okay, sorry. I just want to say before that the neural networks are not limited in the inputs. They could have multiple inputs. Could be n inputs, for example. And they're not limited in outputs. They could have multiple outputs. Could have 3 inputs and 4 outputs. And we may use this in multiple cases. Let's say I'm talking again about the weather. Let's say that the inputs are humidity, pressure, and rain, and wind. Then I'd like the output to be the rainy, sunny, cloudy, and snowy. And I'd like my neural network, ideally, to output for me some sort of probability. And I'd pick the output with the highest probability. And again, I'm always assuming that my neural network was able to find these outputs. Again, the question is how? And let's move... Oh, sorry. Let's move to, I would say, the most important algorithm in neural networks, which is namely called gradient descent. So what does gradient descent does? Take random weights at the beginning. We do our first try with some data and calculate our loss function and get a result. Then we try to minimize this loss function. Calculate the gradient of the function L to W1 to Wn. The gradient gives you the highest ascent. Go a small step in the opposite side, it gives you the deepest descent. Repeat this until you find a local minimum. And I believe that a lot of you are still here first years and don't know what's a gradient. So a gradient, think about it as a slope. For example, if you have a 1D function, we say that this is the slope, right? It shows in which direction is the function going. For example, if I have a parabola, that's the slope. And it's the same thing in multivariable calculus. When you have multivariable calculus, when you have, for example, more than 2 variables, instead of outputting for you a 2D curve, it outputs for you a 3D shape, for example. And the gradient is just the slope of this multivariable function. And for our computer, it doesn't care much. It always knows. It's very easy for him to handle multiple variable calculus. Where it's true that for us humans, starting at more than 2 inputs, we start to struggle. But it's the same thing. So if we follow, for example, the algorithm, we try to first find the gradient. So for example, the gradient would be here. In multivariable calculus, the gradient always gives the highest ascent. That's how it's computed. So for example, if I calculate the gradient in this part, this would be the gradient. Then, the gradient gives the highest ascent. I'll take a small step in the other way. And then I repeat the process, and then I repeat it until I reach the local minimum. And the function that we're trying to find its local minimum is the loss function, which makes sense. We're trying to minimize our loss. We want our loss to be the lowest possible. That's why we try to find the local minimum of our loss function. But the gradient descent only works for one output, because it can only optimize the weights that are mapped to one output. And then you might question yourself, how do we do it for multiple output function? Very easy. How we do it is just consider these 4 outputs neural network as 4 different one output neural network. And then apply gradient descent for each one. And then you will optimize your weights. the problem is that if you notice, the output is always a linear combination of the inputs. I still didn't solve the problem of the machine learning. I still always have linear relation between my inputs and my outputs. So we thought, okay, how do we fix this? After, I would say, years of thinking about it, people came with a very easy solution. I mean, not easy, but it works. Making a neural network with more than one layer. This makes our neural network be able to do, I would say, more complicated functions. Now, the relation is not always linear. So it's linear to this way, linear to that way, and you can imagine that the product of both, for example, both linear combinations gives you a higher degree linear combination. A square, this could be a circle, or parabola, or anything. If you add another layer, this could give, for example, a third degree relation. The problem is that, again, the same question comes. So how is my neural network going to learn? When I explained before, my neural network is only able to optimize these weights. But okay, let's assume I optimize these weights. How am I going to optimize these ones? And then we talk about the most important algorithm in all of AI, what we call backpropagation, the key algorithm. So it happens after each gradient descent. You start from the end and calculate the loss function for our one neuron output. Then optimize the weights and propagate the error to the previous layers. Repeat the same thing with considering again multiple neural networks for each output neuron. Go recursively to the previous layer and the same thing again and again until you propagate the error to the input layer. A bit abstract, but it's pretty simple. Let's say you calculated the error here, for example. Then you calculate what are the optimized weights here. Then you propagate the error to the previous inputs, to previous layer. Then again, you apply gradient descent for each of these ones with the new value that is inputted there. And then do again gradient descent and come back to the input. And I found a very interesting way to explain this, which I called the chief example. Let's assume that my neural network is trying to make a dish. And each of my unit is just a chief that's participating in making this dish. So me, I'm going to taste this dish. I'm going to be like, okay, this sounds not very good. And I'm going to tell each, for example, this one is taking care of salt, this one is taking care of pepper, this one is taking care of meat, this one is taking care of I don't know what else. I'm going to tell this one, okay, you had too much salt. But this one is going to tell me, no, it was this one who didn't give me enough salt. And then it's going to tell him the other, no, it was you who didn't buy me enough salt. That's how it works. You propagate the error from the end to the beginning. And then you optimize again and again until the weights hopefully converges. Very interesting. And actually neural networks are pretty useful. For example, you could use them in handwriting recognition. Handwriting recognition, let's imagine as an image with, I don't know, for example, let's say they have a square and I wrote 2 in it. And the whole image is just a bunch of pixels. You could imagine like that, right? If I told you to make a classical algorithm that will take each of my handwriting numbers and map them to what's the actual number, it's just impossible. Because this is a true, this could be also true, this could be also true. You can't make an algorithm that will tell you for each possible true that exists what's the real number. And that's what neural networks come. What you do in neural networks, you create an input for each of the pixels. Then you input the value of the pixel in each of the units. Then you input it in a very long neural network, and hopefully it will give you some very important output. But all what I told you now is obviously not all of AI, not all of neural networks, not all of machine learning, and not all of probability and uncertainty. There is a lot of ways to make this even more efficient. For computer vision people, they use, for example, pooling and convolution, which means, I would say, to minimize the image, with still making it readable, and which means then that we'll have less inputs, and you have more efficiency. Now, I give you the initial, I would say, the base thing, the ground for AI. The thing that, for example, I need months to learn. Now it's your turn to go yourself and learn it by yourself. To finish this talk, we explored a lot of stuff. We explored the premises of AI. We explored the uncertainty and probability. We explored the world of machine learning, and we finally explored neural networks. There is a very important subject in AI that we call LLM. And what LLM means is a large language model. This would need a whole talk of itself. And very complicated, but I wouldn't imagine a talk about AI if I don't talk about large language models. So I was thinking a lot. How can I make this efficient? How can I make this fun? And I would say more interesting than only just doing another 20 minutes for LLMs, for example. And I thought a very interesting, funny way is that me, with you, I'll try to explain LLM and create an LLM in less than 5 minutes. So Omar, can you do a countdown?
Yeah.
So let's start. So there are 3 things that are very important in LLMs, for example. First thing is what we call tokenization. So what's tokenization? Let's say that I'm inputting a sentence that is, for example, the weather is. I can't input this whole sentence into an LLM. This doesn't make any sense. The LLM wouldn't be able to understand the whole sentence. At the end of the day, computer science is numbers. You can't feed this whole sentence into one unique input. So I need to divide it. That's what we call tokenization. Which means, for example, I could divide this into the, weather, and is. But in real life, it's actually pretty random. You could even divide it as t, and then her, and then we, and then der, and then is, for example. And then you would feed each token, that's what we call a token, you would feed each token into one of the units of the input. Then the second step, which is very important, is what we call embedding. So what's embedding? As I said, computer science is full of numbers. I can't manipulate words in computer science, and my neural networks only accept numbers as inputs. So how am I going to do this? I'm going to try to translate each of the tokens to a possible number. And how am I going to do this? We use what we call vector spaces. I know that a lot of you don't know yet what's a vector space, so I'm going to keep it very simple. Let's assume that I have 2 planes. I have a normal plane, and that this axis express the fact of being a boy. This axis express the fact of being a girl. And now I'm going to express each of the word as a coordinate. For example, if I take the word K, it would be here, for example. And the queen would be here, because it's more a girl. And for example, if I express, I don't know, daughter, it would be here. And son would be here. And you could notice that the differences between these 2 variables is pretty close. Because at the end of the day, it's just a map. It literally expresses how son is a boy and how king is a girl. And it could be for multiple dimensions. You could, for example, add another dimension, I don't know, that explains teaching, for example. And for example, Professor Kinga would be here because she's a woman and she's a professor. And Professor Ovsanikov would be here, for example, because he's a man and he's a teacher. At the end of the day, you then, for example, give coordinates. For example, this means 1. This is 0, this is 1, this is 2, for example. And son would be, for example, the coordinate 1, 1, for example, in our vector space. Then you get coordinates for each of our inputs. Then you express them, and you feed them in our input. And the last step, and very important one, is, I would say, feeding itself. At the end of the day, the LLM is just an input, then a network, then an output. Then, what's going to do? Okay, so let's imagine I'm putting the weather is as an input, the network processes it, and then outputs, for example, is good. But I want to finish the sentence. So what I'm going to do? I'm going to, again, do the same input, then the network, but I'm going to feed with the network the output of the previous network. And then I'm going to get another output, which is going to be, for example, today. And again, another input, another network, and then your other output, for example, you would get a dot to finish the sentence. And that's an LLM. Thank you very much. Question?
Exactly 3 minutes.
Really?
That was shorter, yeah. That was finished.
God. Any questions? Okay.
Actually, have a question myself.
Guess what?
So what I understood basically is that, can you go back to the part about neural networks? Yeah.
You think? Which
one?
one?
We had the loss function.
Oh, it's very old.
Not really. Yeah.
This thing, yeah.
Yeah. So what's happening here?
So it's not a loss function. So for example, this is an activation function. So you input 0 and 0, then I give the weights -1, 1, and 1. Then input it, we get -1, which is our basis, plus 1 times 0, plus 1 times 0, which gives -1, plus 1, which is 0. Then we put it in our activation function. Activation function is 0 is right after the threshold, which maps to 1. Then the output is 1. I mean, no, but the output is no, -1 plus 0 plus 0 gives -1. -1 is here, gives us output 0.
So if I understand this correctly, you have an input that is being inserted, and there is an output that you want.
Yeah.
And to control the output, you use the input, and then you insert it into the model, and then you don't know what output you're going to get.
No, I don't know.
Because the weights are not defined. The weights are being.
The weights are optimized with gradient descent. At the beginning, I don't know. I'm taking random weights.
So if I get a wrong answer, maybe I don't have the right inputs at the beginning, or maybe I have the right inputs but not the right outputs.
Then I calculate the loss.
It's going to be, in this case, it's going to be 1.
Then I calculate the loss with one of the loss functions I said before. So either 0, 1 loss, or L1 loss, or L2 loss. Then I calculate the loss and then use gradient descent and make it and optimize it.
Okay, and then
Repeat.
the weights are updated.
Yeah, the weights are always updated. Okay. Any other question? Yes.
For the vector space, let's take this example. How do we define voidness? Like, how do we quantize it? How do we say that sun is at x equal 1 and things at x equal 2?
So,
equal.
I mean, it's very, very deep, but it basically just means that, for example, so this axis represents how boy you are. And for example, we give coordinates like 0, 1, 2, 3, 4, 5. And for example, you'd say that, for example, sun is here and sun is 1 and 1 in the girl, which doesn't make sense to be honest, but like sun would be like 2 boy and 1 girl, for example.
Yeah, but how can we assign
It's arbitrary.
values?
Like it depends on each model and how accurate. Like it's very, very big. Like normally we'd have like 30 million of dimensions, you know. Like.
Does it still satisfy all the vector space axioms?
Yeah. No. It's a proper vector space. Like it's an actual vector space. Any other question? Yes.
According to what you said, LLM are just basically vectors multiplying, no?
Yeah. At the end of the day, all neural networks is an input vector that you have, and then you do linear combinations, which is basically multiplied by matrices. You want to look at it like that. But that's another layer. Just not really necessary for the sake of the presentation. Any other question? Okay, so thank you very much for coming, everyone. It was nice to see you all.
You should put the last slide.
Oh yeah, true.
The QR code.